All right, so we were looking at example 4.2, and we found our total displacement of the particle from the origin. Now we can go a step further and look at the magnitude of the total displacement and the direction if we would like. So let me go ahead and do that really quickly. So our magnitude of our total displacement would just be the square root of 2 squared plus 0 squared plus 9 squared. Okay, and that will give us 9.2. So that's going to be our magnitude of that displacement vector. And then we can find our direction. And our direction is going to be with respect to the x-axis in the zx plane. So this plane in this direction here. Okay. So what we'll do is we will take tangent inverse of 9 divided by 2, and we get 77 degrees, again with respect to the x-axis in the xz plane. Okay? All right, let's go ahead and move on from that example and now look at velocity vectors. So the velocity or instantaneous velocity vector is going to be very similar to our instantaneous velocity in one dimension. We're just adding on 2 other dimensions, okay? So our v of t is just going to be equal to dr dt, okay? So it's the same exact thing, but now with now in more than one dimension, okay? We can also write it this way, and this is what you will see quite a bit, similar to what we saw back here, okay, for our position vector. We write them in terms of our unit vectors, I, j, and k, okay? So this is a way to write it, and we can denote the different v sub x, v sub y, and v sub z as so, okay? So hopefully this makes sense. Basically, we just break it down, and we can take our derivatives of these 3 different aspects, okay, of the coordinates, okay? And then we can also define our average velocity as so. Again, it looks very similar. And all we're doing is now we have vectors here, okay, to describe our positions. All right, so let me go ahead and do an example with that. So the example 4.3 states the position function of a particle is this, okay, this is what describes it, this equation. And it states what is the instantaneous velocity and speed at t equals 2 seconds. Okay? So what we need to do is we first need to find our instantaneous velocity, and that's going to be a function. Okay, so we're going to have instantaneous v of t. Okay, so this is part A. And remember from our last slide, it's really just dr dt. Okay, so I'm going to take each individual piece here and take a derivative with respect to t. So the derivative of 2t squared is going to be 4t, and this remains in the I hat direction. Okay, then we have 2 plus 3t, so taking the derivative of that with respect to t, we get 3, and remember it's still in j hat, plus derivative of 5t with respect to t is just 5, and this is in k hat. Okay, so this is our instantaneous velocity, our general description in terms of t. And the units are meters per second now, okay? But we want to find it at t equals 2 seconds. So our instantaneous velocity at 2 seconds, we plug in 2 for t, and it's only in this one space. So it'll be 4 times 2, which is 8 I hat, plus 3 j hat, plus 5 k hat. And that is our instantaneous velocity at 2 seconds. Okay. Now it asks us for the speed as well. So the speed is really just, I'm going to label it S. It's really just the magnitude of the velocity, right, without the direction. Okay, so what we'll do is we'll take a square root of 8 squared plus 3 squared plus 5 squared. And so the speed is, put it into a calculator, you get 9.9 meters per second. Okay, so that is going to be our speed at that time, 2 seconds. Okay. All right, the next part of the question says, what is the average velocity between 1 second and 3 seconds? Okay, so now we have 2 different times, and we're trying to find the average velocity. So let's go back to our last slide here and look at that definition. Average velocity, okay? We're going to now be using the position vectors, okay, in order to describe that. So V average will equal R at T1 or 3 seconds, or I'm sorry, T2. T2 will be 3 seconds, and then R at 1 second divided by 3 minus 1. Okay, this is going to be our setup. So what we'll do is we'll plug in our values. Okay, so for each t you see, you'll plug in a 3 first. So let me go ahead and do that. So we're going to have 2 times 3 squared I hat plus 2 plus 3 times 3 j hat plus 5 times 3 k hat. Okay, and this is going to be minus 2 times 1 squared is just 2. 2 plus 3 times 1 is just 3 here, j hat, plus 5 times 1 is 5, k hat. Okay, and this will be divided by 3 minus 1, which is 2. Okay. Then we will go ahead and add these together. So we have 2 times 3 squared, or 18, minus 2, which is going to be 16 I hat, plus 3 times 3, which is 9, plus 2. Okay, so that's going to be 11, plus 5, no, minus 5, I'm sorry. 11 minus 5, so that's 6 j hat. 5 times 3 is 15, minus 5 is going to be 10 k hat, and that is divided by 2. So just divide by 2 in each individual component here, and we get 8i plus 3j plus 5k. Okay, and so this is our average velocity here between 1 and 3 seconds. Okay, and again, you could go further and find your well, I guess not. This is really all that we're looking for in this problem. Okay, so we've got our instantaneous velocity and speed, and then we have our average velocity. Okay. All right, moving on. So this is just an idea we need to remember. It is the independence of perpendicular motions. Okay, so components of vector equations are separate and unique functions and do not depend on one another. Okay, so motion along the x-axis has no part of its motion along the y and x axes, etc. Okay, so if we have motion, okay, so if I drop this ball, this one's red, and I toss, I guess, the blue ball in the x direction. Okay, so this is the x and the y directions. One of these, so this blue one here, has a horizontal motion, okay, and it also has a vertical motion, but the red ball just has the vertical motion, okay? But as you see, they are completely independent of each other. So the motion of the red ball and the motion of the blue ball, they fall at the same point, right? Or the same velocity, I should say. Okay. And this shows that they have the same exact motion in the y direction, even though the blue ball was thrown to the positive x-axis. Okay, so let's see. Motion of an object in 2 or 3 dimensions can be divided into separate, independent motions along the perpendicular axes of coordinate systems in which the motion takes place. So again, I can describe both of these in x and y coordinate systems, okay? And they would be completely separate motions, okay? Just like we were seeing in these other ones. So we had this one here where we had the satellite in a circular orbit. Okay, we had a motion in the y direction and in the x direction, like in R2 here. Okay, we had motion in the x direction and in the y direction. Okay, so we treat them separately and kind of put them together. And that's what we'll be looking at here soon. So another thing I want to mention is instantaneous acceleration. So again, it's very similar to the other two that we already went over, the position vector and the velocity vector. Okay, so we have an acceleration vector, which describes the instantaneous acceleration, and it is going to be the derivative of the velocity vector with respect to t, okay, or the second derivative of the position vector. This should have a z here. Whoops, I'll have to fix that. Okay, so we can write this in 3 different ways here. These kind of spell them out a little more I can't think of the word right now. Straightforward, I guess you can say. We can take each component of our velocity or of our position and take the derivatives that way. Okay, it's just a little bit more straightforward there. Okay, and so we want to start with another example. I can get it started in this video, but I'll probably have to finish it in the next one. So it states a particle has a velocity described by this function here. What is the acceleration function? So our acceleration, again, is going to be the derivative with respect to t of this function. Okay, so it's going to be a of t is equal to dv dt. Oops, okay. So we will take the first derivative here. So 5t derivative with respect to t is going to be 5. This is I hat plus, this is going to be 2t j hat minus 6t squared k hat. And this is now in the units of meters per second squared. Okay, so this is our new acceleration function that we just found. Okay, now we want to find the acceleration vector at a specific point, t equals 2 seconds. Okay, so we will finish this up in the next video.